Good afternoon, everyone. My name is Will Hasting. I'm the Aerospace Solutions Engineer for Velo3D. I'm really excited to come and talk to you today about free-floating technology. This is a technology that has only been available for the plastics, for the SLS process in the past, but now, as of today, we're actually able to capitalize on this ability to print parts free-floating in powder for metal AM. So to start off with, I have a son right now who's learning to ride a bike, and it's a good illustration of sometimes the things that help us also hold us back. And so in the case of training wheels, it helps keep them vertical, but it actually keeps them from using the bike as it was intended. But you know, this is actually a little bit similar to how things are going for metal AM. We have these supports and they help us when the part is within the machine. However, once that part leaves the machine, leaves the 3D printer, it actually is the root of the problem of a lot of the post-processing steps, a lot of the post-processing pain that we have. So I'm going to talk to you today about really how Velo3D's technology has enabled us to basically break through and have this free-floating technology that's going to save you money in terms of the cost of the parts. It's going to improve throughput. That means revenue, simplify your supply chain, and then finally we'll wrap it up with how you can design for free-floating. So this isn't just something that we're doing, but something that you can do yourselves today. So to get started, this is a typical part here, 3D printed part. And you can see it has, most of the surfaces are supported that are under 45 degrees. So this is often known as the 45-degree rule. And really, it causes a lot of material that has to be removed once this comes out of the printer. And this really holds us down. We think that we should be able to print a part and then put it in a box and ship it to the customer, but that's just not the reality of where we've been. So I'm going to step through with you a little bit of why do we need supports in the first place? What's the root of the problem? And the root of the problem is residual stress. So for laser powder bed fusion, it starts off with having a layer of powder and then a laser that comes down and melts that powder into a melt pool. And as this melt pool solidifies, it causes a potato chipping effect that you can see right here. And it causes this contraction, and that residual stress is built up and layer by layer, and that's why you need supports, because it helps basically hold the patient down onto the operating table as you print. So then looking a little bit deeper though, when you get to shallower and shallower angles, the process window becomes tighter and tighter. And so these are the parts that you see up on the screen just to help illustrate. These are discs, 15-degree angle. You can see right here, here's one where the process was in control. So a nice surface finish on both sides. And you can see the same part up there as well. But then if the process goes out of control, say you have too much power and you blast through that melt pool, you blast into the substrate underneath the part, and then you start melting the powder underneath. That's where you have this instability, and that causes really ugly looking parts like you see right here. So process control is a very key aspect to how you overcome the support problem. So how do we remove supports? So there's a lot of creative thinking going on today about how to remove supports. First off, you go at it with a grinder and some safety glasses or pliers. It's a very manual process. And then next you have folks that are using chemicals to dissolve these supports off, another option. And then finally, my favorite option is explosives, where there's actually a controlled explosion within the part in order to remove the support. So it's a fun thing about this industry is that the creativity that people are applying in their day-to-day jobs to try to overcome these issues. So what does this mean, though, once this part comes out of the printer? So let's look at this a little bit more operationally. So first off, you have all this residual stress, so the first thing you do is you send it to stress relief, so heat treatment. Then after that, you wire EDM the supports. Then there's that manual support removal or explosions or what have you that we just talked about. And then finally, it goes to HIP and solution age, so more heat treatments, then final machining. And then, not to mention, that build plate that you just cut off, that needs to be refinished, checked to make sure it hasn't warped too much, because generally build plates are another consumable that you have to worry about and continually track. And let's think about this a little bit more granular, in a more granular sense. What about all those handoffs? And between each handoff, there's a shelf, and that's more technician time that has to be put into that part. So that's more touch time, more people, and then if we think about this a little bit more, that's more floor space, and so you need a larger facility. And then finally, it means more Excel spreadsheets. So, I mean, I love Excel as much as the next guy, but you know, it's not so much fun when you're working in a shop and you're literally having these daily meetings of what parts do we need to get out, what's the prioritization and stress relief, the wire EDM. A lot of times this can be an issue where there's many parts stacked up for wire EDM and you can't get them through fast enough. So all of that coming together, that creates a lot of inefficiency on the post-processing time. So I want to ask you now to think about what the possibilities would be if you were to remove supports. So what if we attacked the root of this issue? So it would short circuit the entire process. You would literally take the part out of the machine, out of the 3D printer, and you'd send it directly to solution, age, and HIP, and then final to machining. So you imagine, like, look at all these zigzag steps that are being removed here by being able to free float the part. And this is all because of supports. So what would it take to look at this a little bit deeper? And there's two key technologies that Velo3D has developed that has allowed us to be able to print free floating. So the first part is, if you remember back to the discs, you need tighter process control. You have to really start to thread the needle more and more on your process and have that comes down to control of your lasers, that comes down to calibration, that comes down to the amount of data you're getting off the machine to make sure it's a stable process. And then also the other key invention here is the non-contact recoder. So remember, if a part is starting, the initial point of that part is free floating in powder. It cannot be disturbed. So you can't have a snowplow of a recoder that's going to go in and just push it off and brush it off into the side. So having a non-contact recoder that hovers above the powder bed is another key technology to enable this. So looking at this a little bit more, so here's an example of where we actually accomplish this. So here's Gene, one of our applications engineers. He's finishing up the build here. You can see the build plate is rising up to the top after the build, and the powder is brushing off the side. And then right here, he's pulling straight out of the powder, boom, supersonic aircraft. So this part right here this is the same part out of that build. You can see there's, first off, no bead blast on this, no sort of surface treatment or anything. What you're seeing is the part as it comes out of the machine. And there's no shift lines. This is really a part that's ready to be fully post-processed, no additional steps. So, and then you can see we all have room for improvement. We still haven't come up with the shelf solution for the need for shelves between operations, so we're still working on that one. But, you know, so I just showed you this novelty of it, but there's actual operational impact to free-floating parts as you remove all those steps. So I want to walk through with you this case of a support of a turbine blade. So first off, on the left side, you can see how the blade is, this is in a Velo Sapphire machine. There's supports there on all the underside surfaces. And You know, my background hasn't been strictly in metal AM, and one of the things that really surprised me when I got into this space is we have a very large Z height, and where I was working, we were only printing a couple inches off the build plate. And the first thing I thought is, what about all that wasted space? If you think about lean operations in a shop, it's all about eliminating waste, and that's wasted capacity, wasted space in our machines whenever we're printing a couple inches off the build plate. So by tackling this problem with free floating, we're actually able to utilize the full build volume. And not only are you using the full build volume, but the surface area per unit, per layer is increased because you're finishing one blade and starting the next simultaneously. There's overlap and they're able to be nested in between layers. And you can see here it takes from 80 parts per build to 450 parts in a single build. So bear with me now as we dive a little bit deeper into the details, because we're going to look at a 4-week month here and understand how does this impact operations. This is for a shop that's running a single shift, 8 a.m. to 5 p.m. They come in Monday morning and they start the machine. You can see with the free floating build, this is a 290-hour build. It goes straight on into the following weekend, so about 13 days. And then you see the 80-part build, and that's a 53-hour build. And it starts Monday morning, same start time, and then the technician on Wednesday has to come in, swap it over, it takes an hour and a half, and then he can continue on. But that second build is finishing late Friday night, early Saturday morning. And it's not reasonable to demand of your technicians that they continually come in on the weekend when they're already doing a 40-hour work week during the week. And so based on that, you basically miss the weekend. And we actually worked this in many different scenarios to try to see if we could game it where we start on a Friday, start on a Thursday, and try to overcome this weekend issue. But with this specific build, basically it's like a game of Frogger, and you're eventually going to get hit by this weekend, and you have to reset on a Monday morning. So looking at this a little bit deeper, this takes your part quantity from 160 parts per week to 225 parts a week. So that means more shop throughput, that means more revenue. So very much a good guy there. Then you can see you have a 34% higher machine utilization, because you're basically, for the free floating build, you're only starting that machine twice a month, and the rest of the month it's just accumulating hours. So 64% to 86% machine utilization. And this has a very big impact on the cost structure of printing that part, because now the fixed costs of that equipment is now amortized over more hours per month. So based on that, your cost per part goes from $123 to $88 per part. So this is a 26% cost savings, and this as well, it's still in the machine. We haven't even talked about post-processing yet. So now bear with me here. So we're going to take this $123 and $88, and then we're going to go into post-processing. So you can see right here we have the different steps laid out here, and we're able to eliminate the wire EDM, the stress relief, and the build plates from this when we go with the free floating option. It also reduces the machining time, and so it goes from about $40 in machine to about $30 is what we're accounting for. Based on this, it takes the total part cost with post-processing from $199 to $126. So this is a 37% cost reduction by being able to free float the exact same part, exact same geometry on the same machine back to back. So really profound stuff. So I've shown you the wowness factor, then shown you the operational impact of why your boss should care about this, but now I want to empower you of how can you design for this. Because this isn't about what can we do at Velo3D in our lab and cool whiz-bang videos, but really how do you apply this day in, day out at your job to empower yourselves. So a couple guidelines here with free floating parts. The first aspect is the part must start from a single point, and this goes back to having the residual stresses in the part. If a part starts at 2 points, the residual stresses are too high when the two parts connect, that it'll cause deformation during the build and most likely result in a failed build. Next, you add stock as necessary, and we'll step through this turbine blade example a little bit more in the following slide. And then finally, follow the other Velo3D support-free guidelines. So we had a webinar a few weeks ago by Brian Spink. He's our applications engineering manager, and did an excellent job where you really see where is our capability today with a variety of different features. So stepping through this turbine blade example, let's walk through the steps here. So first off, in the light blue, you can see where there's some key surfaces that are difficult to print. Difficult to print surfaces really means horizontal surfaces a lot of times in metal AM. So you can see the underside of the platform there is difficult. There's the underside of the dovetail and the bottom side where there's the cooling air inlet holes. So first off, identifies those surfaces, then choose an orientation point. And that's where the build is going to start from the ground up. So for this case, we decided to orient the part at 30 degrees and then start at the leading edge of the dovetail on the ID. And you can see that circled in blue there. And then finally, we added stock here. So that entailed having a triangular piece of stock added between the leading edge of the platform and the initiation point on the part. And then also adding stock on the underside beneath the dovetail to make a nice consistent surface that we can build upon. And then looking at this, and so not everyone's trying to print turbine blades, so we walk through some different examples for you. So one key aspect here is pointy structures such as an inducer, a nose cone. Conventionally, you would have this flat on the build plate and you'd wire EDM off the backside of the inducer and then continue with post-processing. However, if you're free-floating this part, you actually start it at the point, and then that creates a nice initiation point for the build to continue. Then looking at another simple shape, just cubes. There's a lot of cubic structures out there. And traditionally, you would just have this flat on a build plate and wire EDM it off. However, if you just orient the part at 45 degrees, then you can start it from an initial point and continue building from there. So finally, in closing, this opportunity is there for the taking for you today. It's going to increase your throughput and revenue. It's going to decrease part costs, and it's going to simplify operations. And really, the key thing is just learning how to design from point and energizing your engineers so that they understand the benefits of this and they can start thinking about how they're going to orient the part, how are they going to design the part, or how are you going to take an existing part and be able to make it free floating. So, thank you. Any questions? What was that?
Have you found that this method affects tolerances or effective resolution?
We haven't had any. The question just for everyone else is, have we seen any impact on tolerances or dimensional stability in free-floating builds? What we've found to date is that we have not seen that outside the bounds that you typically have with metal AM. Even with supported builds, sometimes you have some distortion based on if you're going from a very small mass or cross-sectional area in a build to a very large. You know, having that large change in mass will impact the dimensional stability, but outside our typical processes, no.
Which is your resolution?
Generally, we say it's within. Sorry about that. The question is, what's our typical resolution for printing? This is very part dependent. What we're able to print just from the thinnest that we can print is, I think I'm getting some feedback there. I'm going to step back on the stage. So typically we're able to print on a variety of structures down to 150 microns. So that's 6 thou. So like in terms of being able to print brass, However, when you start moving to sheets, like if you're designing heat exchangers, then that goes upwards to the 150 to 170 micron range. So it is geometrically dependent. When you get to very large structures as well, and you start to get this shrinkage factor, and that's where we say plus or minus 0.02% of the overall feature of size dimension.
What materials have you tried this with?
Yeah, so the question is, what materials have we currently tried this with? Currently, in both materials that we're printing today, titanium 6.4 and Inconel 718. We've found it a little bit easier with Ti 6.4 to print free floating, but this turbine blade up here that I'm holding, this is Inconel 718, and actually the same thing with this boom plane as well. This is Inconel 718, but we've not found really any constraint of titanium versus Inconel currently. Yes.
Can these parts get so heavy that they fall into powder?
So the question is, can these parts get so heavy that they fall into powder? Fall over? So the part is still being supported by the powder around it, and the powder is in a cylindrical volume, and so there's the powder itself is kind of compacted there in this cylinder. So you'd have to displace the powder, and the powder would have to be flowing out of the volume for that to occur. So the short answer to your question is no, we don't have any issues. We haven't come into any limitations on size yet that we've tried. This, for example, while we're on the subject of size limitations, this is a 280 millimeter tall part, and this is this is the tallest free-floating build we've tried to date. But this is also so this is the tallest build we've tried to date. However, not to say that we can't go a full build volume in Z height. Good question. Any other questions? Okay. Well, feel free to stop by the Velo 3D booth or talk to me afterwards if you have additional questions. Thank you very much for your time today. Looking forward to seeing your free floating designs.